Have you ever seen a function generator that works at 60 gigahertz? This video shows you a way to make this a reality with a single continuous optical fiber. Electromagnetic waves are an essential component of modern society as they play a significant role in areas such as communication, manufacturing, and public safety. We utilize electromagnetic waves to transmit information and interact with matters every day. Applications such as radar and optical communication require us to manipulate the energy content of the wave over time, which is achieved by altering the temporal shape of the waveform. We can accomplish this requirement through arbitrary waveform generation, or AWG, a tool that allows its users to customize the temporal shape of the waveform. To generate a customized waveform, one needs to control the spectral content of the signal. This can be implemented in various ways. As shown in the following example, a light signal is coupled out of the fiber into free space and collimated before it arrives at the diffraction grating. This diffraction grating disperses the signal spatially as a function of frequency, as illustrated by a rainbow of colors. Since the spectral components of the signal are now spatially separated, its spectral amplitude and spectral phase can be modified independently using an array of liquid crystal modulators, which is similar to those used in LCD screens. Afterwards, the spectral components of the signal are recombined at the grating, resulting in a modified temporal waveform. This system works, but unfortunately has a high insertion loss. Because the light signal must be coupled into the free space and then back into the fiber, an insertion loss on the order of 13 dB is typical. Now we will introduce a new arbitrary waveform generation technique that has negligible loss. The waveform generation is carried out in one continuous splice-free fiber. Our system customizes optical waveforms utilizing a discrete spectral line-by-line shaping technique. It employs uniform fiber Bragg gratings that are used to separate spectral lines and provides independent amplitude and phase control for each spectral line via inline polarization controllers and fiber stretchers, respectively. Pulse shaping is carried out in a continuous fiber. The system has negligible loss, and thus can be scaled up to control many lines in order to achieve better shape control. An all-fiber system is robust and low cost, and compatible with existing fiber communication networks. In addition, the fiber-based waveform shaping system can be encapsulated in other materials to protect it from environmental perturbations. Here's how the system operates. First, a continuous wave laser is modulated to generate several spectral lines. Then, the lines are individually reflected by the fiber Bragg gratings. Each grating reflects only one line, as its reflection spectrum is tuned to match a specific spectral line. Since each spectral line passes through a different number of polarization controllers, the polarizations of the spectral lines can be individually controlled. As these lines go through the polarizer, their amplitude will be attenuated depending on their polarization. Likewise, the phase shifter inserted between the fiber Bragg gratings can serve to modify the individual phase of the spectral lines. Working in the optical domain, we are able to generate customized waveforms with bandwidths of 60 GHz, well beyond the 500 MHz limit of electronic AWG instruments. Here are a few examples of waveforms generated using a system we built in our lab. As can be seen, by manipulating only 5 lines, we're able to generate a variety of waveforms. Even better waveform control can be achieved by increasing the number of spectral lines. Thank you for viewing this video, and I hope I have convinced you that a 60 GHz function generator is well within the reach of our technology.